Welcome to Physical Geography lecture series. In this particular episode, I will be talking to you on the theory of isostasy. This lecture also has 5 subunits, namely introduction, where general aspect of the isostasy will be given to you, then followed by specific aspects like concept of isostasy, views of Pratt on isostasy, then that is followed by views on isostasy given by Airy, and the 5th aspect will be the significance of isostasy in physical geography and geomorphology. Earth's crust constantly but slowly undergoes changes and experiences several movements. On one hand, it experiences forces coming from below the surface of the earth, which are collectively known as endogenetic movements, namely earthquakes, volcanoes, and associated movements. Whereas often they are preceded by, the plate tectonics. On the other, there are a set of exogenetic forces operating on the surface of the earth, which wear down the land masses and deposit eroded materials elsewhere, mainly on the ocean floor. Along with these forces, our Earth's crust has another very slow processes which are often difficult to see, and that is isostasy. It is the condition of equilibrium in the Earth's crust maintained by a slow yielding flow of rock materials under gravitational stress. After going through the whole lecture, you will understand clearly that isostasy is not a violent force like earthquake or volcanoes. It is not like a forceful force causing sudden rise or displacement of crustal materials like plate tectonics or mountain building activity, whereas it is another slow process which coexists among all these other forces and movements in the earth crust, but also engaged in bringing macro level equilibrium in different broad sections of the earth. Isostasy is the name given to all these complex forces which keep the varied features of the earth in one balance or equilibrium. The name was given as early as 1889 to this phenomenon by an eminent American geologist, Dutton. His idea was that the high mountains on the land masses can only exist of the rock material beneath them is relatively light. The continental crust of the earth has visible part above the surface and a lower invisible one. The balance between these two is isostasy. At current rates of erosion, about 13.6 cubic kilometers, most of the earth's surface would be flat, but isostatic uplift offsets some of this erosion. If part of the upper surface is removed by erosion, the continental crust will rise to offset these erosion. When land masses undergo this kind of isostatic uplift, the ice sheets or glaciers also, their huge accumulation and subsequent melting too will have effect on isostasy. Some sections of the continental crust have been pushed down by the weight of the glacial ice. The extent of depression varying with the thickness of ice and density of material below, it is believed that the critical size of an ice cap to depress a landmass is around 500 kilometer diameter. At present, we have such huge ice sheets on Greenland and Antarctica. As the concept of isostasy is a complex one, let us view it with some more examples. The state of balance which the Earth's crust tends to maintain or to return to isostatic compensation, if anything occurs to offset this balance, this is based on the principle of buoyancy, first outlined by Archimedes. It is best illustrated by a high mountain basin which rises above the surface of the earth but has to be compensated by deep roots of sialic material, which penetrate deeply into the underlying sima. When denudation lowers the mountains and carries the detritus away, compensation causes the mountains to be uplifted to maintain isostatic equilibrium. So when you look at the other figure which is given in this diagram, you will understand this very clearly. So the huge mountain features, they constitute lighter material which often known as sial, and that has a density of something like 2.7, and as the mountain features rise high in the on the land surface, you will have deep roots penetrating into the magma or the mantle. So whereas this kind of the upper crust is having very thin layer below on the ocean floor. You have to see the figure number 2 carefully, you can understand this in detail. Okay. Because of the deficiency of masses in the oceanic sectors of the crust, the balance is maintained by an increased thickness of much denser sima. Higher continental masses float on a denser substratum. Because of isostatic mechanisms, continental masses which are depressed under the load of ice sheet will gradually recover as the ice melts. This is known as Glacier Isostasy. Similarly, as a great weight of alluvial sediments accumulates at a particular point of the crust, will slowly sink, and sinking takes place because of the isostatic movements also. Now, after knowing briefly about how this isostasy happens in the Earth's crust, now let us come to some of the contributions by two eminent the scholars to the field of isostasy. Now, if you come to the sub-aspect of 3, we have views of Airy on isostasy. Little later, in 1859, Pratt, an English earth scientist, proposed hypothesis on isostasy. Through illustrative diagram of his, which is almost similar to Airy, it speaks about level of compensation under the isostatic equilibrium in the Earth's crust. For this, you have to see figure number 4a and 4b. But his model is based on the use of blocks of different metals, each with different density. These blocks, although of the same cross-sectional size, are cut in lengths such that all blocks have the same weight. The dense metals like silver and lead have shortest blocks, while the less dense metals like iron and zinc have long blocks. See figure number 4a for this. If we now float these in a pan of mercury, they will be all sink in, to such a depth that their bases are at the same level. In force with which such blocks presses down upon the mercury at the base is same for all the blocks. According to Pratt, this level represents the lower limit of the Earth's strength as a rigid substance. It is located at about 100 kilometers deep, whether beneath the mountains or plains or ocean basins. So once again, see figure number 4b in order to see the level of compensation. The material is less dense under the mountains like our Himalayas than under the low plains, and it is most dense under ocean floors. This condition of floating at rest, whether as visualized by Airy or part has since been given the name isostasy from the Greek words isos, equal, and stasio, a standing still. Isostasy, as we understand by now, is merely a state of equilibrium in the Earth's crust. Now friends, after knowing the views of these two great Earth scientists, now let me come to the fifth aspect of the theory of isostasy, that is about the significance of isostasy in physical geography and also geomorphology. Airy, a British astronomer, proposed the hypothesis of isostasy in the year 1855, and it is illustrated by a simple model using floating blocks. For this you have to see figure number 3. Suppose that we take several blocks of a metal such as copper. All blocks have the same dimensions of cross section. They are cut to varying lengths. Because copper is less dense than mercury, the blocks will float on a dish of that liquid metal. If all blocks are floated side by side in the same orientation, the longest block will float with the greatest amount of rising above the level of mercury surface, and the shortest block has its upper surface lowest, with all blocks now floating at rest. It is obvious that the block rising highest also extends to greatest depth. Airy supposed that the material of which the mountains are composed extends down into the earth to form roots. You see the figure carefully, composed of lighter or less dense material. This lighter material, which may be granite rock, protrudes downward into a location normally occupied by a denser basaltic or ultrabasic rock. Upper plain region, the root of less dense rock will be very shallow. Under the floors of ocean basins, it will be shallowest. As just now I mentioned, see the figure number 3b carefully to understand all these things. By applying these basic principles of different sections of Earth's crust and to different landforms gives us the understanding of the distribution of the permanency of land and ocean basins. According to the theory of isostasy, the brittle zone, the Sial, which we already referred to continental landmass, floats at and also at rest on plastic mantle beneath. We have assigned the name lithosphere to that brittle zone, the term asthenosphere to the soft layer beneath the seama, where the Sial has lower density of something like 2.7 grams per cubic centimeter, and the seama has an average density of 3.5 grams per cubic centimeter. Further, erosion processes transport rock particles from mountains to adjacent plains or shallow areas where they are deposited. Once again, as I already explained, you have to see figure number 1 to get the clear view of that. As layers of sediments, they get deposited. Okay. The mountains rise a bit and adjacent plains sinks a bit. Example, our Himalayas and Gangetic Delta region. But in each interval of time, the mountain and plain will reach nearly the same level. That is the crux of isostasy. The mountains, the plastic material of asthenosphere, will flow in slowly to occupy the space vacated by the rising block of course, this newly introduced plastic material rises. It comes into a region of reduced temperature and close to become strong brittle rock, that it becomes a part of lithosphere. Again, you see Figure number 1, how below the mountain land masses, the arrow indicates the pushing of that kind of material into brittle zone to form the part of the earth crust or the lithosphere. Similarly, under the sinking plane, the brittle rock mass is forced down into the region of asthenosphere. But here it is heated and becomes plastic, if forming part of the plastic zone. This excess material at depth must flow solely horizontally to escape, and it's only logical that it will move toward the region under the rising mountains. The level of the base of the lithosphere is therefore referred to the depth of compensation, as we already know it, for it is below this depth that changes the load on the earth's surface are equalized or compensated for by slow flowage of the asthenosphere. See once again the figure number 5a and 5b, you will clearly understand the process, how it happens under the asthenosphere. This figure clearly illustrates how this depth of level of compensation below land masses and ocean basins. The depth of compensation is variously estimated to be formed as shallow depth as 55 kilometers to as deep as 120 kilometers. The diagram clearly illustrates this to you. At present, earth scientists consider about 60 kilometers as working model distance. We can recollect that Pratt considered this at 100 kilometers in his hypothesis on isostasy. Let me, under this last episode, come to another sub-aspect, the aspects that prove the theory of isostasy, like gravity anomalies and isostasy. Having set up the crustal model, the next step is to compute a gravity correction based on the masses of the columns computed according to surface elevation. This isostatic correction is subtracted from the Bouguer correction, leaving a much smaller value known as the isostatic anomaly. If the crustal model is a true one and the condition of isostasy prevails, this anomaly should have zero value. In actual fact, computed isostatic anomalies range from -30 to +30 megauls as a characteristics of the most surface of the continents. These anomalies take the form of small hills and depressions, reflecting place-to-place differences in rock density caused by the presence of superficial rock masses of various dimensions, compositions and structures. On the whole, however, much of the earth crust, both continental and oceanic, is judged to be near isostatic equilibrium. We shall find, however, that certain narrow belts associated with the mountain arcs and trenches have very large isostatic anomalies in both positive and negative directions. In these places, the earth's crust is far from being isostatic equilibrium. Evidences of isostasy. It explains to a great extent the present distribution of land and water on earth. When a part of the earth becomes overloaded with large amount of sediment, as it happens even now in deltas of large rivers like Ganges, Amazon, etc., leads to geosynclines associated isostasy. Because in those areas, when you look at those great deltas, huge amount of sediments on millions of tons are accumulated per year because of erosion, by rivers. Also, as happened during the past period, when part of the southern hemisphere was covered by an ice cap, the crust of the earth sinks where isostasy is associated with the ice sheets of glaciers. The tilted shorelines of Great Lakes of North America and the upward moving of the Scandinavian peninsula are at the rate of 3 feet per century represent the isostatic recovery of the crust of the earth from such weights. There is also another evidence that the Alaskan shoreline is tilting upward and the east coast of Africa is rising at the rate of 7 feet in about 100 years, whereas the eastern coast of North America is gradually sinking. For this, one can see a world map showing some of these zones in order to understand the specific zones under the isostatic balance. Please remember, the land masses and the other parts of the ocean basins too are all constantly under the isostatic balance, not only these regions. These crustal phenomena are linked to isostasy, which is a state of equilibrium that exists in the earth crust. Thank you.